streak across the cosmic canvas. Yet amidst this celestial splendor, one luminary reigns supreme, the sun, our radiant beacon of life. Despite the abundance of stars scattered throughout the heavens, the nearest one beyond our solar system lies over 4 light-years away, a staggering distance exemplified by NASA's Voyager 1 spacecraft, requiring a daunting 73,000 years to reach the star known as Proxima Centauri. How fortunate are we to bask in the warm embrace of our resplendent star, nestled at the heart of our cosmic neighborhood. The sun, in its prime and pulsating with vitality, traverses the tranquil depths of its stable phase, a testament to the sublime harmony of cosmic forces. Yet amidst the sun's daily splendor, questions linger in the shadows of our curiosity. How did the sun come to be? How does it conjure the boundless energy that sustains life on our planet? What is the fate of our beloved star? Embark with me on a journey through the celestial wonderland of our solar system as we set our sights on our friendly neighborhood star, the sun, and unravel the enigmatic tapestry of its existence. The formation of the sun, our life-giving star, is a mesmerizing tale woven within the fabric of cosmic evolution. Around 4.6 billion years ago, within a vast molecular cloud composed of hydrogen, helium, and dust, gravitational forces began to sculpt a future masterpiece. Within this molecular cloud, regions of slightly higher density coalesced, and the cloud began to collapse under its own gravity. As this collapse intensified, the cloud's material began to spin and flatten into a swirling disk, akin to a cosmic carousel. At the heart of the spinning disk, most of the mass was concentrated there at the very center, forming a gas sphere, and a protostar was born. Over millions of years, the protostar continued to accumulate mass from the surrounding disk, growing even denser and hotter. Finally, when the pressure and temperature at its core reached critical thresholds, nuclear fusion ignited, and the sun finally settled into its current state. The outer disk material would form the planets, and the sun would grace them all with light and warmth. The life cycle of our sun has now begun. Classified as a yellow dwarf, our star primarily consists of hydrogen and helium, with traces of various metals comprising the remainder. By mass composition, the sun is 92.1% hydrogen, 7.9% helium, with the remaining less than 1% made up of various metals. The sun stands as the unrivaled titan of our solar system, boasting a staggering 99.8% of its total mass. Everything in our solar system revolves around the sun due to the powerful gravitational pull. In fact, we owe our existence to this radiant giant, as its warmth and light sustain life on Earth. At the sun's surface, temperatures soar to around 10,000 degrees Fahrenheit, but within its core, the heat intensifies dramatically, reaching a blistering 27 million degrees Fahrenheit. This inferno is no mere accident, but the result of an extraordinary process known as nuclear fusion. Within the sun's core, unimaginable pressures generated by its immense gravity forge hydrogen atoms into helium, unleashing colossal amounts of energy in the process. Every second, the sun's core tirelessly converts 600 million tons of hydrogen into helium, transmuting matter into radiant energy. Yet, even the sun's boundless reservoir of hydrogen is finite. In roughly 6.4 billion years, it will exhaust its nuclear fuel, heralding its transition from a main sequence star to a red giant, a dying star in the last stages of stellar evolution. Thus far, the sun has undergone a staggering transformation, converting an estimated 100 times the mass of Earth into helium and radiant solar energy. Yet, as the fusion furnace within its core continues to burn, Consequently, the fusion process accelerates, fueling a steady surge in the sun's luminosity. Presently, this translates to a 1% uptick in brightness every 100 million years, culminating in a 30% surge over the span of the last 4.4 billion years. In 1.1 billion years, the sun will blaze 10% brighter than its current radiance. This amplified luminosity acts as a precursor, not only for a surge in heat energy, but also a sign that a transformative shift will soon take place on our own planet. As Earth's atmosphere absorbs this influx of solar warmth, a moist greenhouse effect looms on the horizon. Later still into the future, 3.5 billion years from now, the sun will be 40% brighter than it is right now. Yet this surge in brilliance heralds a cataclysmic fate for our own humble abode. With each passing moment, the relentless blaze of the sun's rays will strip the earth of its life-sustaining essence. Oceans will boil, ice caps will dissolve into oblivion, and the very water vapor that once danced in Earth's atmosphere will be mercilessly whisked away into the void of space. In this scorching crucible, our blue oasis will transform into a barren wasteland, a sweltering orb reminiscent of Venus's infernal embrace. After all of this, with hydrogen finally exhausted in the sun's core, fusion will come to an end. The inner helium ash that is built up inside the sun's core will become unstable and collapse under its own weight. Extra heat causes the outer layers of the star to expand dramatically, and as the outer layers expand to unfathomable proportions, the once familiar sphere swells into a crimson titan, a red giant, its surface extending hundreds of times beyond its former bounds. Now Earth finds itself teetering on the brink of annihilation. The expanding embrace of the red giant sun threatens to engulf the inner sanctum of our solar system, potentially ensnaring Mercury, Venus, and perhaps even our own cherished homeworld. Even if Earth defies the odds and survives this celestial upheaval, the searing heat and relentless radiation of the red giant will render our planet a barren wasteland, devoid of all life. By this point, the sun has only 120 million years of active life remaining. Within this finite span, a cosmic symphony of stellar evolution unfolds with breathtaking intensity. First, a celestial spectacle awaits as the core ignites in a violent helium flash, where 40% of the sun's mass is swiftly transmuted to carbon within a matter of minutes. In the aftermath, the sun contracts to a mere tenth of its current size, while its luminosity swells to 50-fold. For the ensuing 100 million years, the sun will continue to burn helium in its core, entering a phase where it will undergo a rapid expansion, becoming vastly more luminous. Then, over the course of the next 20 million years, the sun's instability becomes palpable as it sheds mass through a series of titanic thermal pulses, each growing in magnitude and frequency. The sun will lose 45% of its mass this way, literally coughing itself to death as each pulse goes through it. During this time, the sun's luminosity will increase to a staggering 5,000 times its present brilliance, its radius now extending beyond the orbit of Earth. Meanwhile, the outer planets of our solar system will undergo radical transformation. Their icy surfaces will melt as they evolve into dynamic worlds of dense atmosphere and liquid oceans. In the wake of this cosmic metamorphosis, only half of the sun's former mass remains, its outer layers dispersing to form a luminous planetary nebula. As the eons pass, the sun's core, now a luminous ember known as a white dwarf, will fade into the vast expanse of space, its once fierce radiance now a whisper in the cosmic void. Yet in its quiet descent, The sun's like